Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
What determines whether a chocolate bar has a brilliant shine and a clean, satisfying snap? Or becomes soft, dull, and covered with white streaks? Surprisingly, it is not mainly the recipe. The answer is the controlled formation of microscopic cocoa butter crystals while tons of thick chocolate continuously flow through a factory. Industrial tempering systems can process up to 6,000 kilograms of high-viscosity chocolate every hour. Yet throughout this enormous flow, temperature, shear, and residence time must remain precisely controlled. A small process deviation can change the chocolate's texture, appearance, and melting behavior. This is where confectionery becomes serious thermal and fluid dynamics engineering. The process begins with fermented and dried cocoa beans. Before production, samples are checked for moisture, fermentation quality, bean size, mold, insects, and foreign material. Vibrating screens separate oversized debris, magnets capture metal fragments, and aspiration systems remove dust and light shells. Optical sorters may reject discolored or damaged beans using high-speed cameras and compressed air jets. Uniformity is critical because beans of different sizes absorb heat at different rates. If the feed is inconsistent, some beans remain under-roasted while others burn. The cleaned beans, or sometimes the separated nibs, enter the roaster. Depending on bean origin, size, and desired flavor, roasting may occur at approximately 120 to 160 degrees Celsius for several tens of minutes. Heat reduces moisture, loosens the shell, and drives Maillard reactions between amino acids and reducing sugars. These reactions create the roasted, nutty, and caramel-like aromas associated with chocolate. But roasting is also an important food safety operation. The thermal process must reduce harmful microorganisms while avoiding burnt flavors and excessive loss of desirable volatile compounds. Modern roasters continuously monitor product temperature, hot air temperature, airflow, exhaust humidity, and residence time. Some systems combine conductive and convective heating for more uniform energy transfer. After cooling, the beans are cracked into smaller pieces. In the winnower, controlled air velocity separates the lighter shells from the heavier cocoa nibs. The nibs then enter impact mills or grinding machines. Grinding ruptures the cellular structure and releases cocoa butter. Frictional heat melts the fat, converting the solid nibs into cocoa liquor. Despite the name, it contains no alcohol. It is simply finely ground cocoa solids suspended in liquid cocoa butter. The cocoa mass is combined with accurately measured sugar, cocoa butter, and, when making milk chocolate, milk powder. Load cells and automated dosing screws control every ingredient according to a stored PLC recipe. Even a small variation in fat content can significantly affect viscosity and pumping energy. The mixture then passes through 5-roll refiners or industrial ball mills. These machines reduce the sugar, cocoa, and milk particles to approximately 15 to 25 micrometers. Above about 30 micrometers, the tongue can detect individual particles, and the chocolate feels gritty. But grinding too finely is also undesirable. The increased surface area requires more cocoa butter to coat the particles. So smooth chocolate is not created by unlimited grinding. It is created by finding the correct particle size distribution. The refined material now enters the conch, a heated high-shear mixing machine. During the early dry phase, the chocolate may resemble a thick powder or paste. Mechanical shear breaks agglomerates. As additional cocoa butter is introduced, the mass becomes more fluid. Every solid particle is gradually coated with a thin layer of fat. Conching controls 3 properties simultaneously: flavor, texture, and flow behavior. It may continue for several hours. Too little conching leaves acidic flavors and poor flow. Excessive conching can remove desirable aromas and waste large amounts of energy. Molten chocolate does not behave like water. It is a concentrated suspension of microscopic sugar and cocoa particles and fat. It has a yield stress, meaning that a minimum force must be applied before it begins to move. It is also shear thinning. As mixing or pumping speed increases, its apparent viscosity decreases. This is why conventional centrifugal pumps are often unsuitable. Factories commonly use positive-displacement gear, lobe, or twin-screw pumps. Commercial chocolate gear pumps can handle approximately 200 to 8,000 kilograms per hour. Flow rate, temperature, and pressure are continuously coordinated. Pumps, valves, and pipelines may be jacketed with warm water to prevent local cooling and crystallization. If temperature falls, viscosity rises, pressure increases, flow falls, and the entire line can become unstable. Now comes the most precise thermal stage, tempering. Cocoa butter can crystallize into several different structures, or polymorphs. The preferred structure is generally called Form 5. It gives chocolate its gloss, firm snap, contraction from the mold, and desirable melting behavior. For dark chocolate, a typical cycle melts the chocolate at approximately 40 to 50 degrees Celsius, cools it to around 27 degrees, and then reheats it to a working temperature of approximately 31 to 32 degrees. Milk chocolate is commonly reheated to roughly 29 to 30 degrees. Exact values depend on the formulation. Inside an industrial tempering machine, chocolate flows across temperature-controlled cooling surfaces. Rotating scrapers improve heat transfer. The objective is not to solidify the chocolate. It is to create enough stable crystal nuclei to guide solidification later. The tempered chocolate reaches servo-controlled depositors that fill each mold with a precise mass. Vibration tables spread the chocolate into corners and release trapped air bubbles. The molds then travel through a multi-zone cooling tunnel where air temperature, velocity, and humidity are controlled. Cooling too rapidly can create internal stress and poor crystallization. Cooling too slowly reduces production capacity. Moist air can also cause condensation and sugar bloom. As stable cocoa butter crystals grow, the bar contracts slightly and releases cleanly from its mold. Cameras inspect shape, color, and surface defects. Check weighers reject underweight bars. Metal detectors protect the final product. And high-speed wrappers seal each bar against moisture, oxygen, and contamination. What appears to be a simple sweet is actually a precisely engineered multi-phase material. Chocolate manufacturing is the control of 4 interconnected variables. From roasting chemistry to non-Newtonian pipeline flow, every glossy bar is proof that delicious flavor can be manufactured only when thermal science, automation, and fluid dynamics work together.